Okay, so let's get started. We talked yesterday, we talked about turbulence. We want to talk about turbulent combustion, and we started talking about turbulence. What we did was we said turbulence is random phenomenon. We cannot predict it, and we want to make some predictions or understand it or describe it mathematically, but we can do this only for statistical properties of the turbulence. And so we defined an averaging operator, which was maybe an ensemble average. And then we said there is also the so-called Favre average. But here, for now, we'll use the Reynolds average. The Favre average is also Reynolds average, but the non-density weighted average. And then later on, you will see we use the Favre average. But both in their application, both are very similar. So so we started out with this Reynolds decomposition. Reynolds decomposition means we have a fluctuating velocity, and we split this up into an expectation and a fluctuating value around this expectation. And the expectation, that's basically our mean velocity that comes from the ensemble average. And then we said we can try to derive equations that describe the behavior, the dynamics of the mean velocities in a turbulent flow. And from this, we started out here with continuity and momentum equation, and we introduced the Reynolds decomposition, and we did this here for the continuity equation, and we saw that if we do this, then we get the exact same equation also for the mean and also for the fluctuating value. The fluctuating value here is just for, it's just here, we usually don't use this. But we use this, okay? So this just says the divergence of the mean velocity is 0, just like the local instantaneous velocity is 0, and also the divergence of the fluctuating velocity field is 0. And that is because this is a linear equation, and then, of course, you add this decomposition, and then you can split it up into two separate equations. Now, this is different for the momentum equation. In the momentum equation, you have the nonlinear term. And the nonlinear term is here, ui duj by dxi. Or you can also write it like this. Why can you write it like this? Probably everyone knows. But if you have start out here with this, how do we write this? D by dxi of ui uj is equal to ui duj by dxi plus uj times dui by dxi. And this here is 0 by continuity equation, right? The continuity equation is dui by dxi is equal to 0. So we can always, here this velocity with the I, we can always move it inside or take it outside. So this is equal to this, okay? So here we just move it in, because then it's easier to derive here these quantities. And then we introduce the Reynolds decomposition. So we have ui mean plus u prime mean, uj mean, but plus uj prime. And then we multiply this out, and we get these 4 different terms. That's exactly what we did yesterday with the continuity equation. And now we take the average of this. This has time averaging. I always like to think of ensemble averaging. Take the ensemble average of this, and this gives you the ensemble average of these 4 terms. The first one is an average already, so it doesn't change. Okay? The last one here, the last one is just ui prime, uj prime mean. This is a correlation, and the correlation is just like ui squared. It's not exactly like ui squared, but if these two are correlated, then this average of this is not 0. Okay? And then here we have ui mean, uj prime. Mean, that is a fluctuating quantity, and the mean of a fluctuating quantity is 0. Okay? So you see this term goes away, and this term goes away, and we just left with these two terms. Okay, this one and this one. And then here I can take this u outside of the derivative again if I want, but now you see this is an extra term. This is the same term as we started with, but because it's a nonlinear term, now we get an extra correlation here, okay? It's the correlation of the fluctuating velocities. If these are correlated, then things happen. If it's not correlated, then this term is also, if these are not correlated, this term is also 0, and the term is not very important. Okay, so now we can write this equation. You see this is now d by dxi of this tensor, and we have already a d by dxi of a second order tensor, here the viscous tensor, so we just add this term here. And the additional term here, we call it the Reynolds stress tensor, and I tell you in a minute why. All the other terms, here this first term, if we do this to the whole entire momentum equation, the first term is linear again, so you will look exactly like the original term. This one here now has these two contributions, one is here and one's over here. It is a linear term, again, if the density is constant. This is a linear term if the kinematic viscosity is constant, and that's it. So that's why we don't need to talk about these terms, and all that changed is this term. Why do we call this the Reynolds stress tensor or the turbulent stress tensor? So this here is the divergence of a second order tensor, okay? And so this, I can also write this as a symmetric tensor, and then this here also is the derivative of a second order tensor, and it's also symmetric, okay? So it has the mathematical properties of this term and this term are very similar. We know this is the viscous stress, and this is why we say this. So this here, viscous stress, it leads to a distribution of momentum, okay? It just distributes the momentum in space. That's what the viscous stress does. And so, because this has the same mathematical structure, we say this also distributes the momentum in space. So that's what we call this. So this is the turbulent stress, and this is the viscous stress. Both of these, now this is important, this is here du by dt, which means this is the time rate of change of the velocity, or you could say of the momentum if you add the density here. And then the question is, what changes the momentum? Momentum is a conserved quantity, and you see here that you have here a normal stress, which leads to an acceleration, and so on. And these here, what's important to realize, let me say, in a typical transport equation, you can have two types of terms. I mean, in addition to this time rate of change, typically two types of terms. One, or in any balance, one is just transport. You have a quantity that is balanced here, which is momentum, and you might have terms that produce momentum or which destroy momentum. Okay, but we know momentum should be conserved, and then I mean, except for this pressure force term, and then you have terms which are so you have terms that produce and destroy, and you have terms that just distribute in space or move stuff around. Okay. So how do you spot a source term and how do you spot a transport term? I call this a transport term. Transport doesn't produce anything, it just moves stuff around. Okay? This is like the energy. We know energy cannot be produced or consumed, really. You can just, move it around in space. And so this is how you spot it here. If you have a divergence of a tensor, that's always a transport. Okay, because if you can show that this here, the integral of this is just over a certain volume is just equal to the fluxes, that the difference of the fluxes go in and out of the volume. Okay, you can show this mathematically, so very easily actually. So this here is just the divergence of a tensor like this. That's just a flux. And so it's just a transport term. So this doesn't produce anything. It just redistributes the momentum. Okay, so here's the problem. First question is this term important or not? The first thing I could do is I could try to estimate is this term important or not? I mean, maybe from measurements or whatever. You think it's important or not? It is important, okay? Why is it important? Because if you have a laminar jet, take here garden hose, okay? And you have this jet coming out, and it doesn't do very much. I mean, it just goes straight. Like I showed you yesterday in this Reynolds experiment, he had this dye, and the dye at some point it mixes with the surrounding fluid, but it just takes forever. It doesn't mix, okay? That's what this term does. Okay, it's very, very slow. And then once it becomes turbulent, everything's totally different, okay? It mixes like in an instant, maybe 100 times faster, whatever. So this term here, that's what this term does, because there's no other difference to the laminar equations, let's say. So this here must be super important. This is all the difference from laminar to turbulent flow is all in this one term. So this term must be important. Okay. Then the next issue here is, okay, we have an equation now. We have also the continuity equation. We have 4 equations, 3 equations for the mean velocities, and 1 equation for the pressure. Okay? And then the question is, can we solve this? 4 equations. How many unknowns do we have? Well, you could say 5, but the 5th one is a little more complicated. So we have the unknowns we have are the 3 mean velocities, the mean pressure, but then this one also is unknown. We don't have an equation for this. And we don't know how to express this in terms of the mean velocity and the mean pressure. If we had a relation, this here is equal to a function of mean velocity and mean pressure, then everything's good, okay? But we don't, and that's what we call the closure problem in turbulence. This is not just one. Turns out this is a second-order tensor, so it's 9 actually. But because it's symmetric, the 3 upper right and the lower left are the same, so it's 6 unknowns, okay? So now all of a sudden we had 4 unknowns, now we have 10, but we have only 4 equations, okay? That's what we call the closure problem. So, but it's not a big thing. Because we know how to derive equations, we can just derive an equation for this quantity, okay? So this would be 6 equations, and we could just solve these 6 equations in addition, and then everything's good. So let's do that. Here, derivation of a transport equation for this second-order tensor. And this derivation is simple. Take the local instantaneous equation minus the mean equation. That gives you an equation for the fluctuation. Multiply this with this one here by ui prime, and from that you can get an equation for uij, okay? For ui prime, uj prime. So it's not so difficult, and you see there's a little math involved. I mean, algebra, not complicated math. But at the end of the day, this is what we have. This is the equation, and you see a lot of terms here. And here's the issue. So these are all U primes here, UI, UK prime. This is exactly what we solve for here. But then you get this here, which is then called the triple correlation. Now we have equations for all correlations of UI, UJ, but we have now the triple correlation, UI, UJ, UK, which is a third order tensor, and this is 27 individual components, okay? So we started out with 6 unknowns, and now we have like 27, okay? So maybe not a good idea, okay? This doesn't work. I mean, every time you derive more equations, you get more unknowns. That's the closure problem. Why is that? Because in the beginning, we threw away information. We have a fluctuating velocity, okay? So, the velocity can have any value, and there's a distribution function that describes this velocity. And we reduced this down to a mean and a fluctuation. So we lost information, which means, which is why we cannot really close these terms. Okay, so what we have to do, so this just describes all these different terms that are here. Oh, this is what I want to show you at the end. So this just gives you more unknowns than equations. So that's not a good idea, but we could start out with a different equations, and that is the equation for the so-called turbulent kinetic energy. The turbulent kinetic energy is actually the most important quantity that describes turbulence. Turbulence, we said earlier, we can say, maybe we assume, just for simplicity, turbulence is just a bunch of eddies. They have different size, different strength. Strength would be the fluctuating velocity, or maybe, yeah, they're associated with some fluctuating velocity, okay? And the size, okay? And they are, first of all, you have many of these, and also they're inside, so inside each other. So here you might have a big eddy that goes like this, and inside this eddy you have another one turning the other way, and inside of that you have, yet another one that spins yet the other way, okay? So this is how you should, it's a space-filling thing where you have different motions on different scales that are everywhere, okay? So if that's the case, then we can describe these eddies by a velocity, the fluctuation velocity of that eddy, and the size, okay? So two quantities we need to describe these eddies. And if we have two quantities that, if we know these two quantities, of every single eddy that we have, then we can say something about the turbulence. And so this is the first one here. You see the uj prime squared. That's the kinetic energy of the eddy that has velocity fluctuation u, okay? Or this divided by 2, right? So 1/2 u prime squared, that's a kinetic energy. So that's what we use here, the kinetic energy, and that is the kinetic energy in the 3 directions, just, add it up. And I can derive an equation for this and then see what I can do with that. So I can do that easily by going back to this, and I just contract this tensor. I just set k equal to j in this equation, and then I get the kinetic energy equation. Turns out there's an interesting term here. This is called here, so this is the strain of the fluctuating velocity field, and this is the pressure fluctuation, and this is called the pressure strain correlation. And that is, there are turbulence models actually that solve these equations here. This is the so-called Reynolds stress model, okay? Where you solve equations for the components of the Reynolds stress tensor. And in these Reynolds stress models, the most difficult part in modeling is to model this pressure strain correlation. It's a very important term in this equation. And it turns out that if you contract these tensors, this pressure strain correlation goes away. So that's a good thing. And so this gives us here the kinetic energy equation. And you see you have several terms here, and we can, the next slides here, they interpret these terms. We can just talk about it here. So this here is these two together are the substantial derivative, okay? The time-dependent term and the convection term. And then on the right-hand side, now again, there might be terms that produce kinetic energy, consume kinetic energy, or just redistribute kinetic energy, okay? So, turns out this term here is a production term that produces kinetic energy, and it's kind of understandable also. What causes turbulence is a shear, okay? So if you have shear and viscosity, if I have a flow that's here above faster than below, then I have viscosity, then I start an eddy like this, okay? And that eddy, you know, it might break down into smaller eddies, and that's turbulence. So shear on all scales makes turbulence, and that here is just the shear. So the shear times here, you know, some turbulent quantities that produces more turbulence. So you have a little turbulence, and times with shear, it produces more turbulence. And then this one here, epsilon, turns out this is this term here. And let me see if, so this one here I can show, actually I can show easily that this term here is always larger than 0 or 0. It cannot be negative. I can do this by adding this term here once more. And it's not shown here, unfortunately, but if I take the same term and add it once more, and then take half of that, then I haven't changed anything, right? And then for the second term, I just exchange all the indices, and then I can put these together, and I have duj dxi plus dui dxj squared, okay? And because a square, it's always positive. I guess it's unfortunately not shown here, but this is always positive, which means if this is always positive epsilon, and has a minus sign, it must be destruction. Okay, so this is what we call the dissipation of kinetic energy. And then I have this term here, and as I said earlier, you see here on the right-hand side, I have a first-order tensor, 3 terms, but they're all first-order tensor, and I have a divergence of this. And I said earlier, a divergence of a tensor always gives you just transport. So that must be just not producing or consuming anything. That is just you know, transporting stuff around, redistributing. And we can understand it a little bit by here, for example, this term, kinematic viscosity times this gradient. Well, that just looks like a viscous stress. That's just a viscous distribution of kinetic energy. And then we have this term here, u prime times k. So that is something like ui uj uj, you can say, and ui uj uj, that looks like the Reynolds stress tensor for the kinetic energy. That looks like the turbulent transport for the kinetic energy. So that is the turbulent transport that redistributes also the kinetic energy. And there are a few more here, but the point is all of this is just redistribution. It's kind of a viscous or turbulent viscosity. Okay, so this is the dissipation. This just, as I said, this just describes these individual terms, which we have just done. And this might be interesting. This is the budget. So in turbulence, we like to look at so-called budgets. So this here is each individual term in the kinetic energy equation evaluated for a pipe flow. So this here is the center line of the pipe, and this is there must be a wall here somewhere. This here is the wall, I guess. And that's for a pipe flow. No, I think this is I don't know what this is here really. The point is, in a pipe flow, you have on the center line, production is small, not zero. This here must be the wall. If you go to the wall, then the production is zero. But the dissipation is actually has a maximum at the wall. It goes up. That's why I'm confused here. It should actually go up again. If you go towards, if you are at the wall, the dissipation is at its maximum. And this here is free jet. In the free jet, you have, so this here is the radial direction, and this is the center line. And then the production, so this makes more sense here. The production of turbulence is highest in the shear layer. If you have a free jet, the highest shear is not on the center line, not really far away, is somewhere in between. You have a high shear region, and the coffee should not be there, I guess. And so that's where you have production. And then you see the dissipation is here largest on the center line, which means the kinetic energy needs to be transported somehow towards the center line. And that is done here, obviously, by convection. Convection in a jet, because of entrainment, you have convection towards the center line. And so that brings the turbulence to the center line. And diffusion takes the kinetic energy here. You see this is negative contribution here by diffusion, and moves it outwards. And so this was dissipation and production. And then what's interesting is that very often you get regions where all the transport terms are small, and production and dissipation are almost equal. So here, for example, in this region, you see that production and dissipation are almost equal. So that's when you go away from the wall. Okay, so we have this kinetic energy equation, and it's an interesting equation. It shows us something about the dynamics of the turbulence. It showed us that, for example, that turbulence is produced by the mean shear. That's what you see from the equation. It also shows you that, I didn't say that, but if you look at this term, it looks like, or it really comes from this term. This term here is being split up into this and this, with this is again just a transport term. But if you just look at this term here, then you see already this is always positive. And the second thing you see is that the dissipation comes from the gradients in the fluctuating velocity, okay? And that's squared. Now, if you think of what in the turbulence makes large gradients? I mean, you know, how can you spot large gradients in the turbulence? So I could say I have a turbulent flow which has just one scale, okay? Then maybe it looks like this, okay? So this here would be a real turbulent flow. It kind of looks like this, let's say. Maybe it is not real, but you get the point, okay? But then I want to say, here I have large scales and small scales. Let's just look at the large scales. This would be the large scale motion. And this is here velocity fluctuation as function of x, you know, some coordinates, same thing there. So you see the gradients are, you know, this and that. These are the gradients. Now I add a small scale. Let's say I have one small scale and I add this to this, then it will look like this. Right? It's just a superposition of a large scale motion and a small scale motion. And you see that the local gradients, they became much larger. You see this? The local gradients now are very large, where just for the large scale motion, the gradients are relatively small, okay? If I would now add a third scale, which is even smaller, to this, then I would still yet increase the gradients, okay? So the gradients, large gradients in the turbulent flow, they really come from the smallest scale motion. And because this is even squared, it puts even more emphasis on the small scale motion, okay? You could think differently, those of you who familiar with Fourier transform. If you just look at this thing and you do a Fourier transform, then it is something like k squared times u squared. You know, the u hat or whatever you call it. So k squared means k is the wave number, which means this term gets large at the highest wave number. High wave number means small scales, okay? It's the same argument, but if I look at the equation again, and I interpret it a little bit like I just did, then it shows me the dissipation of kinetic energy happens at the smallest scale. This term is important really or it's driven really by the very smallest scales, okay? So that equation tells us a lot, but it doesn't, is not closed yet, okay? So we can talk a little more about, before we move on to closing these equations, we can talk a little more about scales. And in order to understand the scales in turbulent motion, we use certain tools. And one tool is what's called the two-point correlation. So you measure the velocity at one point here, maybe one point x, and then at the same time, let's say, or a little later, it doesn't matter, let's say at the same time, you measure the velocity at another point, x plus r. You know, it's a little bit away from this first point. And then both of these are fluctuating velocities. And you can imagine if you make r very, very large, and I look at the correlation coefficient between these two velocities, it must be 0, okay? If one point is here and the other point is in Michigan or whatever, they are uncorrelated, okay? The correlation is 0. But if you move these points closer and closer together, at some point they move, together, okay? The fluctuation is exactly the same. So the correlation coefficient is 1. So if r goes to 0, the correlation coefficient is 1. And if r is infinity, correlation coefficient is 0. And then, but somewhere in between, it will go from a large value to a small value. And that point where it goes from large to small, that shows me how large the correlated motion in a turbulent flow is, okay? So if I have here a super big eddy that just stands here and turns around, and I measure velocity here and here, they are perfectly correlated, right? They're always correlated. And then if I do this two-point correlation, get perfect correlation, perfect correlation, perfect correlation, and then all of a sudden it drops to 0. And then I know, okay, my eddy here is about the size of 1 meter. So that's what this does, is the correlation at a point x times at a point x and another point, x plus r. You can imagine here that you correlate the same velocity component, ui or u1, or you could also do u1, u2, okay? Or u1, u3, and so on. So this is again a second order tensor that correlates all these velocities together, okay? And r here is r is an independent variable. So the distance between the 2 points is a variable in this, and also the direction, because this is a vector here. The vector can go in all directions. So you see this thing, if you want to evaluate this from an experiment, you have to better measure the entire field in 3D at the same time, okay, at all of this. So in the DNS, you could evaluate this. In an experiment, it's very hard to evaluate this. But anyways, this thing has a lot of information. That's the whole point. I mean, this tells you all the scales you have, because it will not be large and then drop to 0. It will go gradually to 0, and how it goes to 0 tells you how much large scales, small scales you have, and all of this. In what direction, and how are different velocity components correlated. So this here has a lot of stuff. So we can write this then, we can normalize this here by the variance. So the two-point correlation for R goes to 0. If R goes to 0, this is just, and I is equal to J, let's say, then this is just UI squared, right? So we want to normalize this. So first of all, here in this F function, we look at UI, and then we normalize it with the value at R goes to 0, and then it should go from 1 to 0 at R equal to infinity should be 0. And as I said, it just drops to, it starts at 1, and then in some way it goes to 0. So, so that's what we call here the two-point correlation function F. And so F now correlates these two velocities. You take one velocity and the second, the same velocity component at a different point. And these are the velocities that point in the direction of the distance, okay, like this. There's also an autocorrelation function G, which uses these velocities that are normal to the separation distance, okay? But, okay, so from this then, we can define a length scale. We can say, you could now say, well, this is 0.5. That's what I call my turbulent scale. Here, what we do is we say the integral of this function, or the area under the curve. I take the whole area and make it a square here, and that gives me my length scale. We say this is the length over which the turbulence is correlated. Okay, that would give you the largest, the size of the largest eddies you have. And we call this, because it comes from this integral definition, we call this the integral length scale. Integral length scale is a measure for the size of the largest eddies we have. And it comes from this two-point correlation function. From this then, and because we say the velocity fluctuation of these, it comes from the kinetic energy. We can also define a time scale, which then we call the integral time scale, as just the ratio of the length scale and velocity scale. Okay? So now we have, at least for the large scales, we have a measure for how large they are, how, you know, or we have a scaling ratio, how large they are, what the velocity fluctuation is, and what the time is, the time scale is. So if we look at the spectrum of turbulence, let's do an experiment. This is not from an experiment. This is just an artist's view of how this looks like. But you look at this from an experiment, it looks just like this. Now we take this two-point correlation function. It turns out, if now you do a Fourier transform of this, then you get the energy of the eddies as function of their size, or the function of their wave number. So this shows the energy of the individual eddies as function of the wave number here. This axis is wave number, meaning large wave number. So this here my first thing was very small wave number. Wave number is per meter. I mean, is how many waves you have per meter. So the small wave number means you don't have many. High wave number means you have very small scales, okay? So these are the large scales, these are the small scales. So if I look at so this is the log of the energy, and let's just take this as an experiment. Then you see, first of all the energy is in the large scales, okay? Small scales, they might be there, but they have no energy. Remember, this is a log-log plot. So this, if this is 1, then this here is already 0.1. And this here is 10 to the minus 2, 10 to the minus 3, whatever. So in a log plot, all the area, all the energy is just here in the large scales, okay? So that's one thing that is important. We said earlier the energy also is produced in the large scales because it comes from the shear. The shear is a large-scale quantity, so it produces large scales. But the dissipation of the energy is in the small scales. So somehow there must be a transfer of energy from large to small scales. So large scales, they must somehow break up into smaller scales, up to the point where they are dissipated, where they just go away by viscosity. So, so that's what this shows. And so this is what we call here the energy transfer in wave number space. And this region here where this happens, we call this the inertial subrange. And we will see in a minute why this is. Okay, so the most famous works on turbulence is the so-called Kolmogorov theory. He had 3 hypotheses, and he had some very interesting results as a consequence of these, even to the point where he had analytic results from equations. And so his first hypothesis here is the hypothesis of local isotropy. And it says at sufficiently high Reynolds number, the small-scale turbulent motions are isotropic. Isotropic, remember we said last time, isotropic means you have no directional preference. If I do measurements of velocities in this direction or this direction, the statistics will always be the same. Okay, so so he says first of all when the Reynolds number is sufficiently large, and if I look at sufficiently small scales, then they are isotropic. And you see this here. An example is so this isotropy is reached at roughly 1/6 of the integral length scale. Okay, so large scales divided by 6, and these scales, all scales that are smaller, they are kind of isotropic. And you see here, this is from a shear flow. Here you have high velocity on top, low velocity on the bottom, and you see here how these rollers form that I mentioned earlier, where you form these eddies here. But then if you look at the small scale, it'll just look at a small portion. I mean, here you clearly see, this is the fast stream, here's the slow stream. You see clearly the geometry somehow. If I look at this small region here, then I don't see any geometry anymore. It all looks the same in all directions. There's no directional preference here anymore, and so on. So, so that means when we look at just at the small scales, we can treat the flow as isotropic. And I said earlier, for an isotropic flow, the equations become very simple. Okay, let me just give you an example here real quick. I just go back to this equation. How would this equation, okay? How would this equation, the kinetic energy equation, how would this look like for an isotropic flow, for isotropic turbulence? Say it again? All the U's are the same. So the U means here for first of all, they are what? U mean? 0. We said last time, if I have no directional dependence, so this means, no directional dependence means this. I close my eyes, and you spin me around, and then I open my eyes, and I see the turbulence, and then we do the same thing again, and what I see is exactly the same, okay? So if the velocity is going this way, and I see the velocity going away from me. If I turn around, I see it coming towards me, which means if there's no directional dependence, the velocity has to be 0. The mean velocity has to be 0, okay? So if the mean velocity is 0 here, then first of all, this term is 0, this term is 0, and we said there are no, because it's the same everywhere, it's also independent and invariant under translation, then also gradients of mean quantities have to be 0. This is 0, this is 0, this is 0. So for isotropic turbulence, this equation is dk to t is equal to minus epsilon. That's it, okay? So it's very simple theoretical treatment for isotropic turbulence. Okay, so that's a very, very good assumption then. The second assumption, or the hypothesis here, is called the first similarity hypothesis. It says at sufficiently high Reynolds number, small-scale eddies have a universal form. They are determined by 2 parameters, the dissipation and the kinematic viscosity. Okay? How did he come up with this? Well, he wrote the equations here basically for the 2-point correlation. He used structure function, but it's the same. And you know, if you write the equation under this, then make these assumptions, then by just using Buckingham pi theorem, you see how many non-dimensional groups you have. I mean, you just look at this equation, and you see it has two independent parameters, and these are these parameters. So what he did was, he really looked at the equations. And so dissipation and kinematic viscosity. This is interesting, because what this says is if the flow is properly non-dimensionalized, using these quantities, epsilon and nu, I measure statistics of a turbulent flow here in this room. And then you go out and you go to the bottom of the ocean and measure some turbulent flow there. And then you go to the moon and measure a turbulent flow there. And it's all the same. It's exactly the same. As long as the Reynolds number is large enough, the statistics are exactly the same because they're universal, only based on these two parameters. Okay? Isn't that beautiful again? Yeah, that's very interesting. I always get emotional at this point also. Anyway, so what this means, if these are the only two parameters you have, then you can form a length scale from this. Nu cube divided by epsilon. This is now a length scale that characterizes the small scale, the small scale motion of the flow. We call this here the Kolmogorov length, and the Kolmogorov length is a measure for the smallest scale, the smallest eddy in a flow. Anything that's smaller dissipates away because the gradients become too high, and so on. So from this also you can form a time scale and a velocity scale. And so these are the Kolmogorov scales. And what's interesting, if you evaluate the Reynolds number based on these scales, okay, if you say the smallest, or there's one scale in turbulence that has this velocity and this length scale, I can, from these two, I can form a Reynolds number, and it's exactly equal to 1. What does this mean? If I go to larger scales, the Reynolds number becomes larger than 1. So then I go to the more advective limit. And if I go to smaller scales, then the Reynolds number is smaller than 1. That means I really now go to a viscous, maybe even a creeping flow. Okay? That means viscosity becomes very strong. And this is why, exactly or not exactly, for scaling arguments, at this length scale, all turbulent motions disappear. They just go away. Okay, so then the second similarity hypothesis, and that's really the ingenious part. The second hypothesis says, well, if I look at sufficiently small scales that are much, much smaller. Oh, here's my cable, not plugged in. So let's see if this starts up again. So in the old days, when your computer's out of battery and you plug in the cable, it starts up, okay? Then there's some ingenious electrical engineer who comes up with the idea that if the battery dies and I plug it in, you first have to wait for 5 minutes, okay? Because, I don't know, because it makes life easier. Now it doesn't do anything here, really. I mean, usually it at least tells me you have to wait for 5 minutes. Okay, good. So this is the ingenious part. He says if we look at scales that are if we look at scales that are small enough, then they must be independent of the large scales. They are universal, and they only depend on epsilon and nu. Okay? That's what we had earlier. But now it says, if we stick in this limit, but at the same time, we look at scales that are large enough, that are much, much larger than the smallest scales, okay? then they must also be independent of viscosity, because viscosity is only important at the smallest scales. Okay? So this is the joint limit of being really, really small, much, much smaller than this LT, but really, really large, much, much larger than eta at the same time. And if that is the case, then the solution also must be independent of nu, and there's only one parameter that characterizes the solution, and that's epsilon. Okay? Epsilon is the dissipation rate, the rate of dissipation of kinetic energy at the small scales. But let's assume a steady state case for a minute. The energy is produced here at the large scale at a certain rate, which means then the production at the large scale, the transfer rate of energy from large to small scale, and the dissipation rate, they must all be the same if we assume a steady state. So really, we should look at the epsilon here at the energy transfer rate from large to small scales. And then, if that's the case, then I can, bidimensional arguments, then the energy here, if that's only a function of epsilon and the wave number here, then by dimensional arguments, I find that the relation here, E, in this regime, it has to be epsilon to the 2/3 times the wave number to the -5/3. And that, many here must have heard this result before. That is the most classical, most well-known result in turbulence theory, is the -5/3 law, which says in the inertial subrange, that's what we call this, the inertial subrange, because it only depends on inertia, no viscosity. Viscosity is not important, and the large scales are not important. The energy of the kinetic energy changes with wave number to the -5/3. Okay? Very famous result. What that also means then is that if I pick an eddy here, and that's for us is the more important thing. If I pick an eddy here of a certain size, let's call this size LK. So that's just, it's not a particularly large eddy, not a particularly small eddy. We just pick an eddy here of a certain size. That eddy, the kinetic energy of that eddy now, according to this hypothesis, depends only on its size, which is the wave number, and epsilon. That's it. Okay. So I can say epsilon is equal to bidimensional arguments now u prime cube divided by L, and that relation that should hold for each size here in the inertial subrange. Okay. So it gives you a relation between the kinetic energy, basically, of an eddy and its size. Okay? And that only depends on epsilon. So, for example, that's a very, very useful, that's what we call Kolmogorov scaling, and that's a very useful relationship. Because anytime you want to know what's the kinetic energy of an eddy of that size, this is what you use. Okay? So as an example, or you want to know what is the time scale of an eddy of that size, this is what you use. Okay? Because you can also write this as a time scale. So one example is that we say that from these two relations here, you can find the ratio between the largest and the smallest scale. Okay, eta is the smallest scale, this is the largest scale. So that's the scale separation in a turbulent flow. That is proportional to Reynolds to the -3/4. Okay, that's just what it is. And you find this very easily here from this relation. So this Kolmogorov scaling, that's really used a lot, and it's always used, even though very often the Reynolds numbers. So it assumes, of course, that the Reynolds number is basically infinitely large or very, very large. Usually, especially in combustion, the Reynolds number is not very large. Okay. When I said earlier, this is not from a measurement. It's just an artist's depiction of how this looks like. this would be a super high Reynolds number, the way this looks like. Super high Reynolds number mean that the distance between LT and eta is very large. So the distance between these points here and the range of this inertial subrange here is very wide, okay? But in reality, they're much closer together because in combustion, Reynolds numbers are usually a lot lower, and you might not see much of this inertial subrange. Still, we always use these relations that come from this theory, okay? So that's something we need to keep in mind, that you know, we use this, but very often it's not really justified. Okay, so then let's talk about turbulence models. We said earlier that the or is it break time now? Let's see. Or let me just start with this here. We said earlier that this quantity we don't know. What means modeling? So we said the equation is not closed because we have 10 unknowns and we have only 4 equations. So closing means, that's always the same, closing equation or modeling means we have unknown terms and we need to express them as in terms of the known quantities. And what are known quantities? Known quantities are all the equations for which, all the quantities for which we have an equation. Okay? So for example, the velocity u1, u2, u3, we have an equation for these. So I assume these are known quantities. Mean pressure is a known quantity. Okay? So, but these are the only known quantities. So I need to express this in terms of known quantities. Okay. So the easiest and also the most common approach to do this is to say, we said earlier, mathematically, this thing looks a lot like the viscous stress. And because it looks like the viscous stress, it might have a similar way of acting on the flow. And we know, by the way, it has, the turbulence has this effect of distributing momentum very, very fast. And so the easiest way is to say, why don't we model it in exactly the same way? Okay? The viscous stress, we say, is equal to viscosity, kinematic viscosity, times the strain. Okay? So here, why don't we do the exact same thing? Why don't we say this here, this Reynolds stress tensor, is equal to the a viscosity. Now, it is not the kinematic viscosity, this is some turbulent viscosity, times the strain rate tensor. Okay? And that's what this is. Okay? So seems like a good idea. Now there's an additional term here. That additional term is here only to satisfy certain conditions. So first of all, this needs to be negative, or here needs to be a minus sign, okay? That's one. Otherwise, it doesn't have a diffusive effect. It would have an anti-diffusive effect. This here is a symmetric tensor on the left-hand side. So the right-hand side also needs to be symmetric, which is why we say this is the dui dxj plus duj dxi. That's symmetric also, okay? So these are two conditions. And then on the left-hand side here, you have ui, uj. If you contract that tensor, if you set I equal to j, so you have ui, uj. If you contract this tensor, then you have ui, uj. And then ui, uj is equal to twice the kinetic energy, right? And on the right-hand side, we would have dui dxj plus dui dxj, which is equal to dui. So if I contract this tensor, on the left-hand side, I get ui squared. And on the right-hand side, I get dui dxi. What is dui dxi? Is 0 by continuity. So this would say then 2k is equal to 0. That's wrong, okay? K is not 0, it's the turbulent kinetic energy, which is why you have the second term. So this just says minus, so this was minus 2 thirds of K times delta II. The delta II is delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is 3, okay, times 3. The 3 goes away, so minus 2K, minus 2K, okay? So this second term here is just to make sure when I contract this tensor, I don't get a wrong result. Okay, so this is what's called the eddy viscosity model. And again, that's the model that's used almost always. And the interesting part here now is, have we closed the system now? We wanted to close the system, express the unknowns in terms of known quantities. Have we accomplished this? Who thinks yes? I let you go to the coffee break if we have finished this little thing here. Who thinks we have not? Okay. Of course not, because we still have this new t, which we don't know what it is, okay? So new t is one unknown. This year was 6 unknowns, so we have done something. We have done not 90% of the work, but we have done a lot. So we'll continue this after the break.